Garnier from Ecole Polytechnique here today, which will be talking about sequential design for surrogate modeling in Bayesian inverse problems. Thank you so much, Josselin, for giving a talk.
Thank you, Knut and Katja, for inviting me. So for me, it's quite an unusual talk because I will not speak about waves, which is very, very unusual, but I will speak about inverse problems. So I fit within the topic of the seminar. So indeed, the title is Sequential Design for Surrogate Modeling in Bayesian Inverse Problem. This is a joint work with Paul Lartaud, who just defended, and Philippe Imbert, who is a senior researcher at the Department of Energy here in France. So what is it about? Okay, it's about Bayesian inverse problem. So just to make you comfortable, I remind you with a few basic features of Bayesian inverse problem. We are in a situation where we have unknown parameters x, observation y, and we want to understand the structure of the posterior, that is to say, the distribution of x given y, which by Bayes' theorem can be expressed, let's say, is proportional to the product of the prior distribution on the parameters, p of x, and the likelihood of y given x. So in typical situations, let's say when the observation is quite simple, you have an expression of the likelihood that is quite explicit in terms of a forward model. The forward model gives you a prediction of the output given the parameter x. And if you have only Gaussian additive observation noise, the likelihood is just proportional to this expression, where the norm COPS depends on the the observation covariance matrix of your observations. So this is something well known, and we know how to address this situation even in complicated frameworks. Provided we can call the forward model, let's say, as many times as we want. If we are allowed to call the function f as many times as we want, something that can be done readily is to use a Markov chain Monte Carlo method to sample the posterior distribution. And then you can process this sample to get the posterior mean or to get some information about the posterior distribution. So that's all right, as long as I said, you can call the forward model as many, almost as many times as you want. But let's assume here, and this will be the situation, that the forward model, the forward map, F, is very expensive to evaluate. Then you cannot use directly MCMC sampling. That would require thousands or even millions of calls to the function F. So the idea is we would like to replace this costly forward map F by something that is cheap to call, and then run the MCMC algorithm with this surrogate model. But here we would like to do that very accurately and to take into account the fact that the surrogate model that we will use is not perfect. It's not the true function F. So in fact, we have two challenges to solve. Let's assume that we have chosen our favorite surrogate model. You have many choices. You would like to incorporate the knowledge that you know about this, the predictive uncertainty of your meta model. You would like to incorporate this uncertainty into the posterior distribution. So that will be challenge one. And we will see that this one is not difficult if you choose to go with a Gaussian process surrogate model, because this class of surrogate models are very efficient to encapsulate their own predictive uncertainties. So we will be able, indeed, in this setting, to incorporate the epistemic uncertainty on the meta model. So the idea is we will train a Gaussian process surrogate model with some data set, let's say n pairs of input outputs. Then you know everything about the Gaussian process surrogate model, its own rule distribution, and you will be able to incorporate this into, let's say, an effective posterior distribution that you'll be able to sample as many times as you want, and so to run an MCMC algorithm. So that we will see is not too difficult. The second challenge is more difficult, is that often the first surrogate model, the one that you designed, let's say, with the space filling design to learn about the function f, is not good enough to have a sufficient posterior distribution. So you would like to improve the surrogate model to gain some information about the posterior distribution, which means that you would like to make new evaluations of the true function f on some well-chosen points, input points. The question is, which points would you like to use? You would like to use the points that gives you the most information about the posterior distribution. So that's what we want to do. We want to design a sequential design of experiments that will allow me to improve the surrogate model where it matters for the learning of the posterior distribution of my Bayesian inverse problem. This is my target here. And we will see that we want to do mathematics, so we want some guarantees that what we are doing is really optimal in some sense. So we will address essentially challenge 2 during this talk. So first, to make you comfortable, I will remind you about a few basic features about Gaussian process regression. First, let's assume, to make it simple, that the forward model is scalar valued. So the output is just a scalar. And what is a Gaussian process? A Gaussian process is a stochastic process whose distribution is characterized by its first two moments, because any finite dimensional vectors extracted from this Gaussian process will be a Gaussian vector. So you just need to characterize the mean function m of x and the covariance function k to characterize fully the distribution of a Gaussian process. So now let's say we start with some Gaussian process, and we will make some observations. That is to say, we will condition this Gaussian process to go through an experimental design. So you consider points, input points x1, xn. You observe with the true function f, the function f at this input points xi, so you get the value zi, and now you want to condition your Gaussian process with respect to this observation. So what is the distribution of the Gaussian process given this observation? It's what is beautiful with Gaussian process. When you condition a Gaussian process by some equalities, you still deal with a Gaussian process with updated mean function and covariance functions. So you still in the world of the Gaussian process, and you have update formulas, closed form formulas for the new means and the new covariance function given the conditioning. So this is how you can build a surrogate model for the function f. You may say that this is the prior information that you do have. Typically, you don't know much, so we will take a mean that is equal to 0 and a covariance function that we will see characterize the smoothness of the function that you anticipate. And then you will condition this Gaussian process by this data set, and you will end up with a posterior distribution that is fully characterized. So this is just a consequence of the Gaussian conditioning theorem that tells you, as I said, that a Gaussian process conditioned by some equalities is still a Gaussian process. So this is it. Now, what remains to be chosen appropriately is the covariance function that you use as a prior for your unknown function f. And typically, what we will use here is the most classical covariance kernel class, which is a Mattern covariance kernel. So it looks a very complicated covariance function, But in fact, it's complicated in the physical space, in X. It's in fact very simple in Fourier domain. If you take a Fourier transform of this function, you will get something that is extremely simple, that is just a Lorentzian to some power. So it has a very simple expression, but in the true domain, the physical domain, the X domain, this covariance matter function involves the modified Bessel function k nu and some complicated prefactor, but everything is here. And this covariance kernel has three hyperparameters, the sigma squared that you have here. In fact, it's a value of k at x equal x prime. It's the variance parameter. It quantifies what is the typical amplitude of the function that you are trying to evaluate. L is a correlation length. It tells you that the typical scale of variation of f is anticipated to be around L. And nu governs the smoothness of the Gaussian process, of the realization of the Gaussian process. And in fact, the larger nu, the smoother the Gaussian process you are dealing with. In fact, you can show that the posterior mean that I have defined just before belongs to a classical Sobolev space whose index depends on the nu that you have chosen here. So if you anticipate something very smooth, you can take nu very large. If you anticipate something that is rather gross, you will take nu small, for instance, 1/2, which then will have a regularity equivalent to an Ornstein-Uhlenbeck process or a Brownian motion. And so you have these three hyperparameters. Yeah, you can choose, that you can select based on data, actually, by maximizing the marginal likelihood or the log marginal likelihood. So this is something that is well known in the business of Gaussian process regression. There are other methods to select the hyperparameters, but in what we will do today, the maximization of the marginal likelihood is good enough. So this is what happens for Gaussian process regression for a scalar valued function. You can extend this approach to a vector valued function. Now the function f takes values in Rd instead of R. And in that case, you can, in fact, reproduce exactly the same arguments, except that now your Gaussian process is characterized by a mean function that is vector valued and a covariance function that is now matrix valued in values in Rd times d. Otherwise, when you write everything in block form, the formulas are exactly the same ones. The posterior process, given the data, is a Gaussian process, and the update formulas have exactly the same form as in the scalar case. You just have to write things properly. But formally, it's exactly the same thing. So it's just linear algebra formula that will give you the new means and the new covariance function given the observation, given the data set. Now the question is, what type of model? Typically, we will always take m equal to 0. That's the prior information. You don't have prior information, so you take a mean equal to 0. But you have to choose an appropriate form of the covariance matrix here. And in fact, there are different possibilities. You can try a very general form, but then you will have many hyperparameters because you need to characterize the correlation between all scalar outputs. So that's maybe a large number of hyperparameters to select. So you can reduce a little bit the dimension of the hyperparameters using LMC, a linear model of co-regionalization, which allows you, in fact, the principle is to write this vector valued Gaussian process as a linear combination of independent scalar valued Gaussian process. So then you are back to the previous problem, and you just have a little bit more hyperparameters to estimate, but the principle is very close to the scalar valued case, and it gives reasonable results. Anyway, in all the examples that I will show you, it gives reasonable results. You could use another method to address multi-output Gaussian process, but this is the one that is good enough for what we want to do. Okay, so now we know how to build a surrogate model of our complicated function f. So you consider, okay, a data set, pairs of input output, zi equal f of xi, and now you have a surrogate, Gaussian process surrogate model, Zn, to use as a surrogate model for f in the posterior distribution p of x given y. So first thing you could think is, okay, let's replace f by the best estimator of f given the dataset. And the best estimator of f, in the case of a Gaussian process, it's simply mn, the mean given the observation, the dataset that is here. So you shouldn't do that unless you have an excellent surrogate model, that is to say, unless you have a very large data set, because you completely neglect the fact that the MN is just an approximate model for F, and you can really screw up your posterior distribution, Pn, by a direct substitution of F by Mn. So the idea would be to take into account the full distribution of Zn, and so to consider first the likelihood of y given x in which you replace f by Zn. You completely replace f by Zn, and Zn is a Gaussian process with known mean and covariance function. But of course, this is random. So what you do is that you will marginalize, you will integrate with respect to the distribution of the meta model, of the surrogate model. You take the expectation with respect to the distribution of the GP that you do know. So this guy makes sense. And then you substitute that into the formula, into the Bayes theorem, and you end up with a posterior distribution of x given y that has always this form, product of a prior times an effective likelihood. And when you do your math here, in fact, ln is not too difficult. It's the same form as the original likelihood, in which I had C hops here, and f of x there. The only thing that has changed is that you replace f of x by mn of x, the best estimator, and you replace C ops, the observation matrix of the data y, by C ops plus the covariance of your surrogate model Cn at point x. So now this guy depends on x. So here you have a posterior that accounts for both observation noise, COPS, and the surrogate uncertainty. I will not speak about noise, the surrogate epistemic uncertainty, which is Cn. So this solves challenge one. You have a nice expression of the surrogate posterior given an initial data set taken arbitrarily. Okay. Now we would like to improve that. We may be unhappy. You look at, for instance, you can now sample that by MCMC, no problem. You may be unhappy with the distribution. It's not really focused. And so you would like to reduce the surrogate epistemic uncertainty. But you would like to do that in the most efficient way by calling f at new points that are well selected to reduce this uncertainty in Pn. So we will use what is called the stepwise uncertainty reduction method, which is, let's say, a general principle. So when you go back in time, you find, in some sense, the first ideas about this principle almost 15 years ago. So the idea of a SURE strategy is really to design a efficient sequential design strategy, even optimal sequential design strategy with respect to a certain metric of uncertainty. And it was the first time was people started to think that, oops, it would be good to use martingale theory to prove results, to make rigorous mathematical results. So what is the idea? We will only deal with continuous function, and we will look at all possible Gaussian measures on the set of continuous function. Okay? So let's consider such a Gaussian measure on the set of continuous function, the realization of this measure, so it's a Gaussian process. A sequential design, that's a definition, that will be a collection of points, sequential points, such that for all n, xn plus 1 is fn measurable, where fn is information, the sigma algebra, generated by the first n observation. So that means that it's a sequential design strategy to choose where you will call the function f at step n plus 1. You can look at the results of the calls up to n. So you can look at what are the results of f at x1, xn to determine where will be xn plus 1. So you have the right to do that. So now there are many possibilities of sequential design strategies. So consider an arbitrary sequential design. Okay, you can denote by dn the distribution of the GP conditioned by Fn. Okay, we know how to do that. We have just done that before. And now you can consider some metric of uncertainty. We will see some example just after. A metric of uncertainty that quantifies how good is the measure nu n for some objective. So you will have to choose the metric uncertainty depending on your goal. Our goal will be an inverse Bayesian inverse problem. And we will say that the sequential design is good. It will be a SURE strategy if we can prove that h of nu n converges to 0 as n goes to infinity. So this is what we want to do. We want to build sequential designs that respect this definition, which are such that h of nu n goes to 0. So that's our target. So now what is a good metric of uncertainty? Okay, in fact, the first that you may think at is the integrated mean squared prediction error, which is you look at the variance at point x, so it's C nu of x. You take its determinant if it is a multi-output Gaussian process, otherwise you don't take an absolute value because it's always positive. So this is indeed a measure of the uncertainty of your Gaussian process at point x. Okay, you want to have an average quantity, so you integrate this guy over all x with respect to some probability density, and here that would be the prior density on x. So this is indeed a measure of the uncertainty of a Gaussian measure nu. When it is small, that means that the posterior variance is small everywhere where the prior is. Okay, so that's an easy one. But in fact, this is not a good one for us, because what we want is to have a good posterior distribution, a good estimation of the posterior. So we want this variance here to be small, not where the prior is large, but where the posterior is large. So now that makes sense. That is indeed a good measure of uncertainty for what we want. But the problem is that it's much more complicated. Because here, nu is just here, and you have seen the update formula for the covariance of a Gaussian process. It's very simple. It's just linear algebra. So it's easy to compute this guy, as long as you add new points, new observation points. It will be easy to update C nu and to understand what happens. Here it's much more complicated because now you weight this variance by something that depends itself on nu and in a more complicated way. So the new dependence of this metric of uncertainty is much more involved than the original one. So nevertheless, this is the one that we want to study. This is really our metric of uncertainty that will tell us whether we are good or not. So now, in general, what is a good, let's say, metric of uncertainty? It's something that would satisfy the following property: a new evaluation reduces h. It's a measure of uncertainty, so when you make an observation, you should reduce the uncertainty. So we will only work with this kind of metric of uncertainty, and we will say that this guy here can be expressed in a mathematical way according to this definition. We will say that the metric of uncertainty has the supermartingale property if for all Gaussian measure nu and for all input points x, this quantity is smaller than h of nu. And what is this quantity? It's in fact the measure of uncertainty of the measure nu, but conditioned by I make an observation at x. So here you can see that this is a measure nu conditioned by I make an observation at x that gives me the result z. So this is a Gaussian measure with updated formulas for means and covariance. But I want to average that with respect to z, because that depends on z, and I want only something that depends on x. So I take an expectation with respect to z that follows the distribution, the Gaussian distribution with the given mean and the given covariance. So that's indeed something that expresses this quote, a new evaluation reduces h. Indeed, when I make an evaluation at x here, I reduce in average the metric of uncertainty. So that's an important property. And with that, I will be able to define exactly what is the Strur strategy, a Strur strategy. The idea is that if, okay, we are at step n with a Gaussian measure nu n, so remember, nu n is the original measure nu conditioned by, hopla, the observation up to time n, up to step n, a sequential design will be choose xn plus 1, which minimizes this guy. What is this guy? Is the anticipated reduction of the, or let's say the anticipated new metric of uncertainty of the measure nu n conditioned by I will make an observation at xn plus 1. Okay? So that's really what ensures that hopefully I will reduce very quickly the metric of uncertainty. So now you may say that you can combine the two definitions. If H has the supermartingale property, then since Xn is a sequential design, the expectation of, let's say, H of nu n given Xn plus 1 is the expectation of H nu n given Fn, and it's something that decays. So it is a supermartingale. So H nu n is an Fn supermartingale because I have this property for all x, and now I take xn plus 1, the Strur strategy, which is Fn measurable. So indeed, I have this decay. I have the supermartingale characterization. So now I'm very happy because H is, let's say, H of nu n is a supermartingale and is bounded from below. H is positive valued. My metric of uncertainty is positive valued. And I do know that when I have a supermartingale that is bounded from below, it has to converge, almost surely. So I have the proof of the convergence with these ideas. Now, there remains a little bit of technical details to show that not only it converges, but it has no other choice but to converge to 0. So here you have a little bit of additional mathematics to prove it. You have to check a few technical conditions, but the main idea is really this one. We have found a super martingale and a positive super martingale, so we have convergence of the metric of uncertainty of the sequence of Gaussian processes or Gaussian measures nu n, and at the end of the day, we show that it converges to 0. So now let's look at our metric of uncertainty, the one that we would like to address. So as I said, it's a little bit complicated, and even I can express it as a little bit more explicitly in terms of the prior, the likelihood, and a normalizing constant. Usually we don't care about the normalizing constant because it's a constant. So for MCMC, it plays no role. But now we look at this quantity, h nu, as a function of nu. And bad luck, this guy depends on nu. And that's a mess. Because we tried, that was the first thing we tried, prove that h nu has the super martingale property. And in fact, it's not true. It's wrong. It's not true that this guy has a super martingale property. So it's hopeless. But now we know that it's wrong. We even have a counterexample. The quantity that has the super martingale property is something that is very close to this one, but you remove the normalizing constant. You take the same thing as the one you have here, but you remove the normalizing constant. So you again have the variance, the likelihood, the prior, but you don't have the normalizing constant. And it turns out that this one has a good super martingale property. So in fact, it's a non-normalized integrated variance. It is still good because it still focuses where points where the variance and the likelihood are large, which are really the points that we are targeting. And it has the super martingale property. This one has the super martingale property. So now we are happy. We have a super martingale property for one design. So now we will be able to introduce the sur strategy. You define dn of x sequentially by the definition, that is to say, d of nu n given x and zn plus 1, which means you observe at x zn plus 1, and you integrate with respect to zn plus 1 given by its distribution. So this is dn of x, and the sur selection rule is to look after a point xn plus 1 that minimizes this quantity. So that's tractable, as we will see. Like that, it seems a little bit complicated, but in fact, no. Because when you use GP surrogate update formulas, in fact, no, it's not so complicated. dn of x is just this quantity, where Cn plus 1 is in fact the GP covariance after conditioning at the observation of x. Why is it so suddenly it becomes much easier? It's because you have a very nice property of the GP conditioning theorem that tells you that the posterior covariance, when you look at what is the posterior covariance of a Gaussian process given an observation of x, does not depend on the value that you will observe. The posterior mean depends on the value, but not the posterior covariance. And that simplifies a lot the algebra. And that's why you get an explicit expression, almost explicit expression of dn of x. It's an integral, but here everything is explicit here. We know we have an analytic expression for everything. So that seems correct to express dn like that. Now you can say that it's an average of this posterior variance here when x star is integrated with respect to this quantity divided by the normalizing constant times the normalizing constant. So you may say dn of x can also be expressed like that. And here you say, but shit, the normalizing constant has reappeared, but it does not matter because we are only interested in the argmin. So now this is really a constant. In terms of x, this is really a constant, so you just have to look after the minimum, the arc minimum of this expression. So now you can really build the algorithm, This is the expression of dn of x. Remember, the dn plays no role because we will only look after an argmin. The Cn plus 1 has a very simple update formula. This is a classical update formula for posterior covariance for Gaussian processes. So it's very easy to compute. And the PDF Pn, that is here, is known up to a multiplicative constant, because indeed it's a product of the likelihood times the prior. So you can sample with MCMC this distribution. And then you have an approximate expression of dn of x divided by Cn, which is the empirical average of this posterior variance, average over x star sampled according to MCMC sample. So that's something that is fully explicit. You see the update formula here, and you see this approximate expression of dn of x divided by Cn is completely explicit. You can do that very efficiently. And now you can choose xn plus 1 as the arc minimum of this sum here. And that gives you a new point that will be almost optimal. Why almost? Because I have replaced dn by something that is not exactly dn, but I can refine a little bit the sur strategy and say that if you have an almost sur strategy with an error here that is decaying to 0, then you still have the convergence of the super martingale theorem. So it's okay. So that's it. You have now a very nice algorithm. So just to summarize, now with this sur strategy here, this one, by choosing sequentially xn plus 1 like that, which is easy, you are sure that your metric of uncertainty will converge to 0. So now you have the proof, and it's based on this super martingale convergence theorem again, plus some additional ingredients. In particular, now you have to restore the convergence of the normalizing constant, but this one is not a big deal because you can show that the normalizing constants converge to a finite non-zero limit, so it does not perturb the convergence of the super martingale after dividing by Zn. Okay, and eventually, okay, you can show that now you have to make at least one assumption on the function f. It's sufficient to say that the true function f is continuous, and then you can show that the posterior distribution that you have built with this sur strategy converges to the true posterior distribution, P, in particular in total variation. You may use the different norms, but this one is good enough. Okay, so that's the algorithm. You first initialize a Gaussian process metamodel, surrogate model with, let's say, a space filling design. There is no point to choose something else, with a limited, a very limited number of initial points. And now you will enrich your surrogate model to target the posterior distribution. And so you have at each step of the loop here to do a MCMC algorithm. So that's a little bit painful, but you do an MCMC on a function that is explicit. I mean, it only involves the mean and the covariance of a Gaussian process, and you know everything. So it's very simple to sample an MCMC of a length of a few thousand, tens of thousands, even hundreds of thousands. That's very quick. And then with a unique sample of MCMC, you can minimize the n of x. And then, once you have selected xn plus 1, you call the expensive model f at this point xn plus 1, you update the GP with this observation, and floof, you repeat. You go one step further in the loop. And you have to stop. So stop when you are happy. As usual, the stopping criteria depends on your real target, what is really what you want to do. So the stopping criterion is, let's say, in some sense, user dependent or objective dependent. What type of error do we want to avoid? So now I will show you a few in 10 minutes, yes, a few, let's say, experimental results. So first, I will compare different strategies and to show that indeed the one that we have introduced is the best one. And we will test the different test cases. So the most usual sequential design strategy is the D-optimal strategy, which is very simple. You look at the point X where the variance is maximal. This is the point where you have the maximal uncertainty in the domain. It makes sense to call the function f at this point to reduce the uncertainty in this region. That will give you a lot of uncertainty reduction. But of course, it's a standard one, but it's not tailored to our inverse problem. It's a little bit stupid if x is very far from the support of the posterior density, because, okay, you will reduce the uncertainty of your meta model in a region that is completely useless. So what you can design is, let's say, a refinement of this D-optimal strategy, where you will look after the point that maximizes the variance, but only in regions that are close, let's say, to the maximum a posteriori, or the one that is known at step n. So indeed, that reduces the search space. So you will focus on a more appropriate region. There are two problems here. Is that first, it's a little bit simpler, not so much, but yes, a little bit simpler nevertheless than the strategy we have designed. There is no MCMC algorithm here, but there is a search algorithm. The problem is that there is no convergence guarantee. This one has no super martingale property or whatever, so you cannot guarantee that you will converge. And on the top of it, there is a tuning parameter, which is the h here. So we will see that it gives reasonable result if you tune properly the h. That's another sequential design strategy. In fact, that's the one that I have described at the very, very beginning. It is the posterior variance integrated with respect to the prior. So this one, it turns out, has a convergence guarantee, but for this metric of uncertainty. So it's not tailored for the inverse problem, but at least you have another strategy. And if you look at the literature, you can find, in particular in this paper, another strategy which tries to minimize another loss function, which is in fact a variance or a quadratic L2 error of the likelihood estimate. So it only focuses on the fluctuations of the likelihood and tries to minimize it. So that makes sense. Again, problem is that this one is in fact as complex as IPSU, and there is no convergence guarantee. It's not a super martingale. And now you may want to test these different strategies with respect to different metrics. So here let's say metrics, not metrics of uncertainty, quality of the performance, say. Of course, the first one you want to test is the metric of uncertainty itself. So here you really hope that you will be very good for this one, because this is the one that you have minimized. So at least you should be very efficient for this one. But you can also test other metric of performance, the posterior entropy, that tells you if the posterior density is close to a Dirac or very broad. And you have also something that is usually not accessible, which is a KL divergence between the posterior density that you have at step n and the optimal posterior density. So it's okay if you know the true function f, then okay, you know this one and you can compute this guy explicitly. Otherwise, you cannot make it. But here I will start with two toy models for which f is very easy. So I will be able to compute this guy. And so, as I said, you can compare our strategy, the one that you have introduced, CSQ, which is this D-optimal but restricted to more focused region, the standard D-optimal, the standard I-optimal, and the Bayes-risk minimization. Just to let you know, in all example, I start the initial design set is very small, it's only 10 points. And then I use the strategy, the sequential design strategy. So these are the first, this is two test cases. So here you can see the posterior distribution in 2D. So I'm not in a high dimension so that I can visualize everything. And these are two typical examples, one in which you can see that the posterior density is a little bit degenerate. You see the support is, let's say, essentially on a manifold. And here is another example in which the posterior density is bimodal. You have two local maxima. So these are two, let's say, non-trivial situations. And in this case, you can compare all methods, all sequential design strategies with respect to all performance metric, Kullback-Leibler, entropy, and IVAR, which is our metric of uncertainty. So of course, IPSure is optimal for IVAR. That's it's designed for that. Huh? But it's also very efficient for all other strategies. So here you can see that, for instance, D-optimal does very poorly, but I would say it's normal because it's not focused on the inverse problem. It's a criterion that is reduce the uncertainty everywhere. The other ones are reasonable, but okay, IPSure is better. And here is just to show that the Sinsbeck, that is to say the Bayes-risk minimization, well, it does reasonably well as CSQ, provided you tune the parameter h appropriately. So you need to run several times the sequential strategy to tune the optimal h. It's not so easy. But if you can tune the h, it's okay. So here it seems perfect, and this was for the banana. So the banana is the one that is unimodal, but a little bit degenerate. Now you can look at what happens for the bimodal situation. So again, here you can see that, okay, the D-optimal does very poorly. The other one seems to be quite good. What is surprising is that the Bayes-risk minimization fails. So you see a CSQ well calibrated and IPSure, they are almost equivalent here. But the Bayes-risk minimization really fails. And in fact, this is something that we have observed when you have to, let's say, sample. When you deal with a multimodal posterior density, the Bayes-risk minimization may really focus on one mode and forgets the other one. And so at the end, it's completely wrong. So this is something that we have observed. While, okay, IPSure has a guarantee of convergence, so of course, it converges. So that was the last example. In fact, this is the example that motivated the whole analysis. So this one is much more involved. I mean, we have real data. The forward model is a very complex neutronic code. So it's a transport code. So as you know, it's the radiative transfer equation. It's in 3D. It's quite complex to solve. It's in phase space. It's and you have the energy on the top of it. So it's an 8-dimensional partial differential equation. So it's quite complex. That's why when you want to identify very, very quickly a nuclear material, you cannot run an MCMC algorithm. But you can run the IPSure, and this is just to show you, okay, here, this is a reduced model. In fact, this is not the full model, where the input parameters are dimension 4. And here you have two-dimensional marginal, just to show that the posterior distribution, you see, it's like the banana case. Uh, it seems to be unimodal, but with a support that is degenerate. It's a kind of okay, two-dimensional manifold in a four-dimensional space. And here, when you compare the different algorithm, again, IPSure seems to be the most efficient. CSQ, well calibrated, does reasonably well. And here, the Bayes risk minimization does well. I mean, not as good as IPSure, but it's quite reasonable. Probably because this is a unimodal posterior distribution. In that case, Bayes risk minimization seems to do well. So these are the experimental observations. Of course, IPSure and CSQ, well calibrated, outperform the classical design strategies, but this is normal because classical design strategies, they don't focus on the posterior distribution. They want to reduce uncertainty everywhere. This is not what we want to do. CSQ is a little bit cheaper than IPSure, and it can be competitive, but you need to fine-tune this hyperparameter H. So eventually, it's not so cheap. And Bayes risk minimization can be okay, but only for single mode posterior distribution. When the posterior distribution is more complex, multi-mode, it can be trapped. Just before conclusion, an extension. In fact, you can introduce another metric of uncertainty, which is what we call the tempered IPSure. So the only difference compared to what I have done is to introduce power beta on the likelihood, beta between 0 and 1. Why? Because it covers the classical IMPSE when beta equal to 0 and the IPSure when beta equal 1. And in fact, you can prove everything with this guy. So I have not done it because that would give an extra parameter in the proof. But in fact, the proof is written with H beta for a fixed beta. So everything is all right, everything works. You can show that the type sur criterion, once you fix beta, is a sur sequential design strategy with guarantees of convergence. But I have not shown it here because we tried, and on all the test cases we have tried, beta equal 1 is optimal. So we don't have proof for that, but that's an experimental observation. So, okay, that's the end of my talk. So just to summarize, so this IPSure sequential design strategy seems to be a very nice way to do surrogate modeling for Bayesian inverse problem. You can really improve your surrogate model by choosing the points selected by this strategy. And in fact, that's good empirically, we have seen that, but that's also very good for a mathematician because you play with the martingale theory, so you have some fun to do some martingale theory and to prove convergence results for the strategy that you have designed. So of course, there are still some limitations. As I said, you need an MCMC sampling. And when you go to a high parameter dimension, when X is very high dimensional, MCMC sampling will require tens of thousands, hundreds of thousands, millions of points to reach, let's say, the stationary distribution. So that may become too cost. Even if a call to GP is, may say, is free, it may start to be quite expensive. As I said, you can extend a little bit this strategy with this tempered IP-sure strategy by choosing beta that would be a function of n itself. So the idea would be to start from beta equal 1. No, sorry, from beta equals 0, the standard strategy. You try to reduce the uncertainty a little bit everywhere, and then you increase progressively beta to focus more and more on the posterior density. Again, in the examples we had here, we discovered that take beta equal 1, right from the beginning, has always turned out to be the best strategy. But why not? Then, okay, we could also think about multi-fidelity models. This is especially true for the neutronic problem that we wanted to address, because the code, the expensive code, can be run at different level of accuracies. Very high level of accuracies, but that's very expensive, or lower level of accuracy, it's still expensive, but less expensive. So how do you allocate the budget optimally in this case? And so, of course, once you have discovered this relation with the martingale theory, you can use the whole theoretical framework and derive rates of convergence and hopefully finite sample guarantees. So now you are free to open your favorite book about martingale theory and use all the theoretical results. Okay, it's time for me to stop and to listen to your questions. Thank you.
Great. Thank you so much, Josselin, for a very, very nice talk. So indeed, the floor is open for questions. So please unmute yourself and ask questions if you have questions.
Hi, Josselin.
Ah, hi, Onkai.
Yeah, thank you for the talk.
You're
I
welcome.
have two naive questions.
Hmm.
So, on the very beginning, you mentioned there are three hyperparameters, sigma, L, and nu.
Yep.
Uh, does that change with the new addition, or that was
No,
fixed?
no, no. No, no, that's it's just to fix a simple covariance structure. You could use something simpler, for instance, a Gaussian kernel, in which case you have only two parameters, the variance and the correlation length. Or you can use something more complicated, but there is no point. So here, okay, it mostly depends on the smoothness you anticipate about your true function f. If you think that your function f is very, very smooth, you could simplify that and take just a Gaussian. Sigma squared exponential minus x prime squared over L squared. That's enough.
So what I'm saying is this is prefixed before, when you're adding new data, you still use
No,
those.
no, okay. No, you can update that. Maybe not at at every step, but after, let's say, 5 steps, you can re-estimate, the hyperparameters. This
Okay.
is typically what is done. You update the hyperparameters, not every step, because usually one additional observation point is not enough to perturb the estimation of the hyperparameters. But after 5 or 10 new observation points, you may think that, oops, now I can try to improve a little bit the selection of the hyperparameters of the covariance kernel.
Okay. So that still belongs to my first question. So the new, in my mind, could be an important parameter because it's really saying, yeah,
Yeah,
if
here the
you
new is the most important one. It really governs the smoothness, and as you can see, the RKHS, I mean the space in which the posterior mean lives, depends only on nu. It does not depend on L or on sigma squared. It just depends on nu.
but in practice, how people, I can see sigma and L is relatively simple to optimize in terms of
Yeah.
optimization. How do you optimize new? If new is, you would probably like new to be,
In fact, usually we cheat. We don't consider nu as a continuous parameter, but when nu is an integer plus 1/2, the knu takes a very simple form. It's an exponential times a polynomial. And in fact, we just select new amongst, let's say, 1/2, 3/2, 5/2.
Okay.
And beyond 5/2 is very close to the Gaussian.
Yeah. Yeah. Okay. So that's a very empirical parameters to
That's,
choose.
yes, yes, yes.
Yes. Okay. The second question is in your later interesting algorithm, you have this trying to find the best new point.
Mm.
Can you give a rough idea how complicated that or simple that optimization problem is?
Well, here we use a dual annealing optimization, so it's not completely trivial, but it's this guy as a function of x is cheap to call. So a dual annealing, which is a little bit intensive again, makes the job very quickly.
Very
So we
quick.
use a dual annealing algorithm to solve that.
Okay. Yeah, because it's remind me people in the old days, not old days, people even probably doing now. It's a radial basis method. They try
Mm,
to approximate functions without mesh, just a radial basis function.
mm.
Yeah, the one thing of that is the air conditioning. So in a sense, all these Gaussian bumps are highly correlated. So in a sense, if you using gradient descent method to solve this,
No, no.
probably
Yes, yes, yes. No. That would be a bad idea because indeed there are several local minima, and you want really to select, hopefully, something that is close to the global minimum. But you need to be close to the global minimum.
okay.
So
Okay.
that's why you use something dual annealing or differential evolution or even simulated annealing could do it if you, but it's not so as efficient as dual annealing. But you need a stochastic algorithm, a stochastic global optimization algorithm. That's
And the
important
initial
to get
guess count.
the neighborhood of the true global minimum. But you don't need to get exactly the global minimum. You need to be close, and that's enough. Because we also have this quasi-sûr that tells you that it will be good enough.
Okay. So where does the initial guess come from?
Here,
Either X and yeah, when you minimize this, you get some probably some simple estimate of the initial position and then optimize a little bit, I guess.
yes, you can always, yeah, okay, there is always this trick. You use this stochastic algorithm to be in the right, let's say, basin of attraction of the global minimum. And when you see that, okay, it seems to converge locally, then you can run quickly a descent, gradient descent. But again, here it's not, we are not after the exact location of the global
Best.
minimum. If we are close enough, it's good enough.
Okay. Thank you.
Good. Any other questions for Josselin? I was wondering a little bit, Josselin, so you mentioned the first step is sort of the space filling points. Couldn't
Mm.
you go with the sequential all the way? Why did you choose, or how would you choose N0? Would it relate to the roughness, for instance, or how is the space for the?
N0? Ah no,
Yeah,
here we chose, I think it's, in all example, it was 10.
yeah.
And it's a little bit arbitrary. That's the minimal number, let's say, that gives you a way to first estimate the hyperparameters that we were discussing.
Ah, okay. Yeah,
You need something to start with. You need a first Gaussian process. Then you will
right.
improve, but you need something to start with. You cannot start, I mean, directly from the sequential design. That
Yeah,
is not possible. You
right.
need to start
Yeah,
from something.
to have some,
But
yeah,
something with 10 points,
yeah.
even with this distribution, is enough.
So in your example, how were the meta parameters chosen? They were based on these 10 points and then you estimate them?
Yes, yes. And as I said, every 10 iterations, we re-estimate the hyperparameters, and
Right.
that's good enough.
Yeah. Great. Thanks. any other questions? Otherwise, let's thank Josselin again for a very nice talk.
Thank you.